please begin.
Yes. Well, thank you very much for inviting me to this conference. It was my pleasure to be in Osaka last time. I think it was a few years ago. So I remember very well the uni where you are now. Well, unfortunately, I can't come to you in person this time since right now we have week 4 of our usual semester. And for instance, today I speak all the day for marking. Well, some of you may understand that it's difficult for me to come to you in person. Well, a topic of my talks will be sort of some basic ideas of, so not basics, but basics ideas concerning three-dimensional integrability. Well, basic ideas may be elements. So elements. So like Euclidean time. And today is 9 of February. Well, so outline of my talk. I think I'll try to give a rather wide approach to all ideas which appear in three-dimensional integrable models. Overview of all ideas, it means that I'd like to start with discussion about classical models in three-dimensional space-time. Classical models means it mostly must be partial differential equations. While then, later, I will proceed to classical models on 3D lattice, which means classical models in discrete space-time. So it could be not partial dE, but discrete diff. P difference equations. And then observing some ideas on the level of classical difference equations and observing idea of canonical quantization, I will proceed to quantum models in three-dimensional space-time. And usually people associate quantum models with quantum tetrahedron equation. But quantum tetrahedron equation will not be the main subject of my exposition. It will appear as a side result. Well, in all these approaches that I mentioned today, classical continuous, classical models on lattice, as difference equations, and quantum models, well, I think basically I'll focus on the origin of all these models on auxiliary linear problems. To my opinion, this is most important part in 3D integrabilities. And then on classical levels, I'll continue with equations of motion. Then we will observe Hamiltonian structure. It means Poisson bracket, which give us a clue for quantization. And also integrability as Liouville integrability of equations of motion. They are closely related to the integrability of all models. So now you see in red boxes main ideas which I'd like to present in my talks. Well, then let us start. And we start with 3D integrable models or integrable classical models, partial differential equations in 3 dimensions. Well, and I start with standard notations. So we consider 3D x vector, x vector, that's usually element of R cube. It has components x1, x2, x3, and in what follows alpha, beta, gamma will be any permutation of 1, 2, 3. Later we will see number 4 as well. And also standard notation could be like partial derivative d alpha. That's just d over dx alpha in a rather simple way. And then starting point for 3D models. By the way, I will talk about a model which is called sometimes on the top, you can see its name, 3 waves resonance system. That's modern name of this model. But this model has very old origin. Sometimes it's related to Darboux and Lamé. It means that what I'm talking about right now, it's 150 years old stuff. Well, and starting point is auxiliary linear problem, which you see right now on the mid of our screen. So here d alpha is partial derivative. Psi 1, 2, 3, that's auxiliary linear variable. Oops. So psi 1, psi 2, psi 3, they are functions in R cube. So that's auxiliary variables. And A, alpha, beta, A1, 2, and so on, 6 of them, they are fields. Well, that's very simple auxiliary linear problem. And why we need linear problem? Since from linear problem we can derive equations of motions for fields A as a consistency condition for auxiliary linear problems. And let me just demonstrate you briefly how it works. So I will use empty page. In my PDF file, there is a lot of empty pages for such demonstrations. So we have auxiliary linear problem like d alpha psi beta equals field A beta alpha then times psi alpha. Please remember, no summation. We don't accept Einstein principle. No summation. Alpha beta gamma is any permutation of 1, 2, 3. And then try to do d alpha d gamma applied to psi beta. And as a first instance, we compute d gamma firstly, then it will be d alpha of A beta gamma psi gamma. Then, taking derivative again, we will obtain d alpha A beta gamma psi gamma plus A beta gamma A gamma alpha psi alpha. I don't understand what happened. How to rotate it back? It happened first time in my life.
Probably you press Control R for rotate.
Control R. I
No,
tried, but
you tried.
it seems it doesn't work.
So if it's just this page, I think it's okay. We can still read it.
Okay. Then I'll continue writing on this page. So now try to do it again, but in opposite order. D gamma of d alpha psi beta. I just exchange derivatives. Then it's d gamma applied to a beta alpha psi alpha. Then d gamma a beta alpha psi alpha plus a beta alpha a alpha gamma psi gamma. And what we saw before it used to be d alpha a beta gamma psi gamma plus a beta gamma a gamma alpha psi alpha. So now we have to equate results. And in which sense equate? Equate multipliers near psi alpha separately. D gamma a beta alpha must be a beta gamma a gamma alpha. So in this way, we obtain equation of motion. So that's origin of equation of motion. You see equations of motion, indeed, they appear as a consistency condition for auxiliary linear problem. So this equation of motion, they are appeared. And what's important in these equations of motion, why they are selected, why they are so interesting for me, for instance. Point is that these equations of motion, they can be obtained by variation of Lagrangian. So that's Lagrangian equations of motion, and Lagrangian you can see on the bottom of this page. Well, just verify that indeed it works. I'll try to write right above this page what could be dl over dA 32. So A32, that's here and here only. So variation becomes very simple. D1 of A23 minus A21 A1, 3, and variation must be 0. You can see that it's exactly our equation of motion as required. And you can verify variation with any other field A. The result will be the same. So first thing we obtain, that's Lagrangian equations of motion. That's a sort of field theory. Then scroll down. If we have Lagrangian equations of motion, then immediately we can proceed to Hamiltonian form of equations of motion. So how to define a Hamiltonian? To define Hamiltonian, we have to understand what is time. Well, here on the left, you can see one of many possible ways to introduce time in this 3D system. Well, unfortunately, definition of time is not relativistic invariant, but anyway, we can define time in this way. Well, and after such one of many possible ways of definition of time, we also can define to split all fields to pairs, A and A star. A and A star, it means that they could be conjugated variables in the sense of, or conjugated fields in the sense of classical mechanics or classical field theory. Well, then Hamiltonian is presented here. So you can see this piece that's potential. Sorry. So this potential. Same potential as you saw before in Lagrangian, but in Lagrangian we have negative potential as required. And in front you have a kinematic part which involves only spatial derivatives dx and dy. And by the way, no spatial derivatives for A2. Then equations of motion correspond to this Hamiltonian in its usual form. Time derivatives, they are result of Poisson brackets over fields with respect to this Hamiltonian, where, so that's expected same time Poisson bracket. Same time, therefore here no prime at all. Time must be the same, otherwise it doesn't work. Well, we see that this is Hamiltonian system. And our equations of motions, in fact, they are Hamiltonian equations of motion. Please remember, we have 6 fields. So 6 A alpha beta, 6 of them. And they include fields, 3 fields, and 3 conjugated fields. And equations of motions are of the first order, as it should be in Hamiltonian equations of motion. But then interesting question is, what is Lagrangian form of equations of motion? To find Lagrangian form, we need to understand, firstly, what is Legendre transformation from Hamiltonian fields, Hamiltonian variables, to Lagrangian variables. Lagrangian variable is H. And proper relation between Lagrangian field H and Hamiltonian field A is the following. Well, we have only 3 H fields, H1, H2, H3, as it should be for Lagrangian equations of motion. Number of variables must be twice less, exactly twice less. And instead of first order equations, we obtain second-order equations. And number of second-order equations must be twice less, 3 instead of 6. So that's second-order equations of motion for Darboux system. Sometimes it's called Darboux-Monakov-Zakharov. Why it's called Darboux-Monakov-Zakharov? Because details I found in Monakov-Zakharov papers. Well, Lagrangian equations of motion are cubic. So why they are cubic, you can see H beta and H alpha in the denominators. When you multiply by H beta, H alpha times H alpha, H beta, then resulting equations of motion will be cubic. Second order homogeneous cubic equations. Well, what is known about this? As I mentioned, that's 3 equations, all second order, all cubic, and one can show that from the point of view of people who are doing solitonic equations in 3-dimensional space-time, that's Kadamtsev, Petviashvili, Kairaki in general position. And now, I think 2 remarks worth to be mentioned. One remark is due to Lamé, Darboux, and other French guys who lived 150 years ago. They didn't start from auxiliary linear problem. They start from something different. They start from Riemann geometry in 3D space with rather simple metric. So that's formula for metric. You see that this formula corresponds to the metric G. By the way, alpha beta, we use notations alpha beta, not I. And here also must be alpha, must be alpha, must be alpha. G alpha beta, very simple form, H1 square, H2 square, H3 square, and rest zeros. Diagonal metric. Then, using principles of Riemann geometry, starting from this diagonal metric, you can obtain easily Christoffel symbols, capital gamma, that's Christoffel symbols, this one and this one. Christoffel symbols, they are just logarithmic derivatives of h. It's not difficult to show. And please remember, our initial fields, A alpha beta, it's not logarithmic derivatives. They are different. So logarithmic derivatives I denote as A tilde. That's also fields, but not the same fields as before. And then one can derive Riemann metric tensor, complete Riemann metric tensor with 4 indices. And now look at the shape of the form of this Riemann tensor and surprise. Condition of vanishing of Riemann tensor is exactly our Lagrangian equations of motion. So therefore, when we talk about zero curvature representation, that's indeed zero curvature representation of certain Riemann geometry. Surprise. Interesting. That's one remark. But there is one more remark. One more remark is related to what is called Chern-Simons Lagrangian. Now, what you can see on the screen, that's standard Chern-Simons field Lagrangian. And I am talking about SU2 Chern-Simons Lagrangian. So that's its standard form. Capital A, it belongs to gauge group SU2. And therefore, we can decompose it. And for SU2 generators of gauge group, that's just sigma matrices. That's written here. Just sigma matrices. Pauli sigma matrices. And it's well known, Chern-Simons Lagrangian is invariant with respect to gauge, generalized gauge transformation. So that generalized gauge transformation is here. And we can use this gauge degree of freedom in order to exclude, to make zero some components of gauge field. Namely, for A1 capital, we exclude T1. So A11, T1 must disappear. Excluded, T1 disappear. For A2, we must exclude A22, T2. This guy also disappear. We can always choose such particular gauge. And here we exclude A33, T3. Also is excluded. And in this particular gauge, Chern-Simons Lagrangian literally becomes this Lagrangian of the three-wave resonance system. So what we are doing Chern-Simons theory. But what is the difference between Chern-Simons and theory that I'm talking about is that in Chern-Simons usually, so what people are doing in Chern-Simons usually people consider equation of motions corresponding to the variation of diagonal elements A11, A22, A33. Therefore, number of equations of motion in Chern-Simons theory is just twice bigger. Not twice bigger, 1/3 bigger. In Chern-Simons, we have extra equations that do not appear in our case. And truly speaking, I don't understand what's going on from the point of view of Chern-Simons theory. It's just a remark, just observation. Well, and that's just half of story. Now, second half of story concerning classical theories. Second half of story is that for the same Lagrangian equations of motion, we can find another different Hamiltonian picture. Different Lagrangian and different Hamiltonian. And how it works. So remember that we start with linear variables psi. So remember that linear variables, auxiliary linear variables, well, and we can also introduce another field psi, scalar field, with no index, which is related to auxiliary variables psi in a certain way, not very difficult. Such change of variables, introduction of field psi is well defined. Well, after this, we introduce fields A tilde, which are logarithmic derivatives of fields H. Usually they are called Lamé coefficients. And remember, these A tilde, they are just Christoffel symbols. I mentioned them before. And also we could introduce one more scalar field rho, which satisfies second order differential equations, where right-hand side is just product of fields A tilde. Some symmetric combination, also such system is well defined. Well, And then we introduce scalar field phi, which is related to field psi introduced before by some simple exponent, sort of gauge exponent. And after this final step, we introduce fields B alpha beta, which are related to Christoffel symbols, but with simple shift with the help of field row. And after some algebra, after some calculus, what will happen? It will happen that newly defined fields B and phi, they satisfy completely different form of auxiliary problem. Now, instead of vector field psi, as we had before, we have scalar auxiliary field phi. And auxiliary linear problem for this field phi is second order differential operator applied to phi must be 0. So that's new linear problem. Well, and in a similar way as we discussed before, self-consistency of new linear problem provides equations of motion for newly defined field B. Please remember that new linear problem, it includes only B. We can forget about A tilde, H, and so on. So newly defined field B. And that's equation of motion for field B. They look similar to previous equations of motion, a bit more complicated. And what's interesting, it's again Lagrangian equations of motion. Lagrangian equations of motion, and that's second Lagrangian for the same system. So remember that Lagrangian variable in both cases, that's just H, which satisfies equations shown on previous page. So Lagrangian equations of motion are the same. Well, that second Lagrangian, you can see that change of variables is non-trivial. It may be non-linear. Newly defined potential is different, but we can define Hamiltonian and Poisson brackets in the same way as before. So therefore, it means that Darboux-Monakov-Zakharov equation written here, these equations simply have two completely different Poisson structures and two completely different Hamiltonian forms. That's interesting. People saw it before in 2D, but I don't remember exact reference. Well, and one more property of equations of motion that we obtained. Well, what will happen if in addition to 1, 2, 3, we also try to use 4, x4, fourth dimension? Let us try to do it. It's interesting. D4 of D1, A, 2, 3. We remember equations of motion. D1, A2, 3, it's A2, 1, A1, 3. differentiate again, and now I'm taking equations of motion into account immediately. So that's A24, A41, A13 plus A21, A14, A43. So that's the result. And what will happen if we permute derivatives d1 and d4? d4, A23. That's d1 of A24, A43. Result A21, A14, A43 plus A24, A41, A13. Now you can easily observe result is the same. So system, our system is 4D consistent. So some people call this situation 4D consistency. But other people call this situation tetrahedron equation. So 3D consistency and tetrahedron equation, in fact, it's the same. So now what you can see on whiteboard, my drawing, my writings, that's just proof of tetrahedron equation in the most simple form. First of all, in classics, and secondly, in continuous space-time. Here, on the bottom of this page, there is one small remark. Similar situation also exists in 2D case. Maybe some of you know this. For some of you, it may be a surprise. Something similar exists in 2D, but in 2D, you have to consider two different equations. So this equation is called modified Korteweg-de Vries. And this one is hyperbolic sine Gordon. And you can easily verify these two equations are consistent. Consistent in this way. And this consistency indeed can be obtained from usual standard quantum Young-Baxter equation. But Young-Baxter equation in the form RLR from such one. That's just comment and small surprise. Well, so tetrahedron equation. For field B, it's the same. Absolutely the same, no difference. Well, and what lessons we learn from classical continuous integrable models, two theories? First thing that we learn is that in general, we can talk about two types, not several types, two types. Two types of auxiliary linear problem. One linear problem is vector, when we have triple psi1, psi2, psi3. And another linear problem may be related, maybe not. We don't know yet. That's scalar field phi, single scalar field. What else? When we are lucky with a proper choice of time, then we expect appearance of Hamiltonian structure and Poisson. Well, Hamiltonian structure, it means Poisson structure. Poisson brackets and so on. And if we're lucky enough, if we are doing everything correctly, then tetrahedron equation at some point will appear itself as a side result. So that's also, I think, important observation that tetrahedron equation will come itself. Well, and now we can, so what's time? Time is 11 past 6. Yes, we can start classical systems on lattice. Situation when we simply replace x vector, which used to be an element of R cube, to vector n, which is element of just Z cube. Discretization. So that's now our point on a lattice, discrete space-time. Everything is discretized. Discretization is always very good. And in what follows some time, I will use notation, for instance, E1 vector, that's just basis vector with components 1, 0, 0, and so on. And also, straightforward idea is just to replace continuous derivative by just a difference, just a simple shift. So now delta alpha will stay for simple shift in alpha's direction. And also understand that I did misprint. It could be not delta, it could be nabla. Well, some people prefer delta, some people prefer nabla. It's very difficult to satisfy all requirements. So therefore, I will leave notation delta. And I beg your pardon, delta instead of nabla. Well, then, elementary example. What we start with? We start with trivial auxiliary linear problem, which is vector 1. And what we can do, we can replace straightforwardly derivative by difference. Replace derivative by difference and then bring this piece, such piece, to the right. Well, and then here you can see straightforward generalization of auxiliary linear problem to the case of lattice, discrete space-time. But then what's interesting? Always it's interesting to rewrite such auxiliary linear problem in very specific, in a specific form. So we have two directions on lattice, alpha and beta. And what elements we could have? We could have on a 3D lattice psi alpha of n at some point, psi beta of n at some point, and also shifted. And psi alpha is shifted in beta direction, and psi beta is shifted in alpha direction. So therefore we have 3 points on the lattice, and in total 4 linear variables, psi alpha, psi beta at point N, and psi alpha, psi beta and shifted points. And sometimes it's convenient to place them as follows. Well, you can see cross, just cross. What cross stands for, you will see later. It's just result of section of cubic lattice. Well, then point N is assigned to one quadrant of the resulting cross or resulting vertex. E alpha is associated with transition through alpha line. So this transition corresponds to shift from N to N plus E alpha. In a similar way, transition through beta line result is replacement N by N plus E beta. And therefore here you can see N plus E alpha plus E beta. That's just some combinatorics. Then auxiliary variables psi, they are associated to the edges of this vertex. Psi beta of N, so this, for instance, this edge or this line is beta line. And on the left, corresponding linear variable is psi beta on N. On the right, psi beta of N plus E alpha. So N here, I'll better use green color. And N here. Well, and after this, that's convenient to represent auxiliary linear problem as a result of matrix multiplication. Matrix multiplication, I mean this one. Well, so what you can see there? Right-hand side. Yes, right-hand side. That's right-hand side. Psi alpha of N plus E beta and psi beta of N. So on the right-hand side, now in green, that's ingoing edges to this vertex. On the left, you can see outgoing edges of this vertex. And matrix X is very simple matrix. That's written here. Just matrices corresponding to this coefficient, and maybe to some algebra. Why some algebra? Since according to my choice, what is green and what is red, what is ingoing and what is outgoing. That's the result of simple algebra. And in what follows, such matrix X is associated with vertex. Well, how it works? in what follows. Such matrices are convenient to write down lattice equations of motion. And lattice equations of motion, graphically, they can be presented as a Young-Baxter equation, equivalence of two triangles. And as a matrix product, they can be written in such interesting and particular form. But it's not straightforwardly Young-Baxter equation, so we need some details. Well, how it works? It requires explanation. Lines are alpha, beta, gamma. We need to introduce auxiliary variables. For instance, here psi gamma, psi beta, psi alpha. I don't use notation argument n, just abstract notations. And outgoing will be psi alpha prime, psi beta prime, and psi gamma prime. Then combination of these are matrices X. Outgoing linear variables like this. It will be result of application of something to the ingoing variables. Now look at this picture. To obtain outgoing, we need to apply a matrix X. Here it will be matrix X1, here matrix X2, and here matrix X3. Well, each matrix X is just 2 by 2 matrix with, for instance, matrix elements A, B, C, D. You saw in our case, particular case, A is 1, B is this, C is this, and D is this. A, B, C, D just for shortness. Well, X1, it exists for alpha and beta lines only. A1, B1, 0. C1, D1, 0, 0, 0, 1. X1 doesn't take into account line gamma, only alpha, beta. In the block gamma, it just identity matrix. Well, then matrix X2, it could be A2, 0, B2, 0, 1, 0, C2, 0, D2. That's X alpha gamma number 2. And last matrix in my picture is X3. It intertwines only beta and gamma lines. Therefore, for alpha, it must be identity. So that's beta gamma 3. Well, and in general, equation, which looks like Young-Baxter equation, for graphically it's indeed equivalence of two triangles, not a problem. But in components, it again looks like what is called local Yang-Baxter equation, but it's understood in the category of tensor sum of linear spaces. So it's not tensor product as for usual Yang-Baxter equation, but tensor sum. Well, and traditionally, I prefer to call this equation Kharipanov equation, since Kharipanov is the person who first told me about this. And this equation appeared in his papers. Well, and yes, just Kharipanov. All Kharipanov equations are always local. Well, and in our case, equations of motion, local equations of motion, has a form of local Kharipanov equation. So there's alpha, gamma, beta, gamma, blah, 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 with lattice argument n plus e alpha, n plus e beta, n plus e gamma, well, appeared according to our conventions, our pictures, and so on. And by the way, such equations can be solved and presented in explicit form, but explicit form you can see is a bit misleading. So you can't extract shifted fields to one hand side and unshifted to another hand side. They're mixed. You can see n plus e gamma and n plus e beta on opposite sides of equal sign. They're different. Well, well, I think, look, now it's 6:30, and I think we could stop today. And I beg your pardon, for today, I didn't take into account possibility of questions. I hope I will have questions next time.
Thank you very much.
My pleasure.